Most students memorize O of n, O of log n, O of n square, and they don't understand what exactly they are talking about. Today in next few minutes, that confusion will end forever. I am going to teach you time complexity in a way that you will never find it confusing again. Go ahead and take a look on various competitive programming websites and you will find majority of the people writing code, then that code is getting time limit exceeded and then they look at the solution and try to optimize it. Well, we are going to change that. We are going to compute time complexity even before writing the code itself. So let's try to understand the importance of time complexity. The efficiency of an algorithm is important in competitive programming. Usually, it is easy to design an algorithm that solves the problem slowly. But the real challenge is to invent a fast algorithm. Time complexity estimates how much time code will use in terms of user input. That's why we are representing time complexity as a function of size of input. Time complexity is generally denoted as O, that is big O notation, of something. So this something is function of n, where n is going to be size of array or the length of the string. Depends on the problem that you are solving. We are going to take a look on various cases so that we can have clear understanding on time complexity. Based on just this definition, it's not sure what exactly we are going to do. But just remember, the main important thing is that it tells you how much time code will take to execute in terms of size of user input. Okay, let's dive deeper. How exactly are we going to calculate the time complexity? See, the very first thing is constant time. We represent constant time as O of 1. But what is constant time? When running time of an algorithm doesn't depend on the input size, then we say the time complexity of that piece of code is going to be O of 1, constant time. It is usually a direct formula or basic operations like addition, subtraction, multiplication, conditional checks, right? Assignment operations. Simple as that. Look at this function f of n. It takes the value n and it returns n into n plus 1 divided by 2. Now it doesn't matter what is the value of n. Yes, the return value, the answer for this function is going to change. But total number of operations are going to be 3 only. We are going to multiply, we are going to add, we are going to divide. That's it. No matter what value you pass for n, the number of operations are not going to check and the time it's going to take is not going to change. Right? That's why the time complexity of this particular function is going to be O of 1. That is constant time. Just remember this. This is very important. People usually confuse in this section only. Constant time doesn't mean that it's not going to take a time. Yes, it will take a time. But that time is not going to be dependent on the input size. See, this multiplication, addition and division is going to take some time. But that time is not dependent upon the input size. That's why we call it as a constant time. Makes sense, right? No matter what you pass here, the value of n, it will multiply, add and divide. That's it. And it will return the value. Finish. I hope this is clear. I highlighted this multiple times because this is where the people make mistake most of the time. They confuse this constant amount of time with no time at all. No, it's going to take a time, but that time is not dependent upon the input. Now the second most confusion is a loop. So look at the very first function, a function f that takes an input n. Then there is a loop that we have and we are performing some kind of operation inside a loop. Look at this operation, this is assignment of operation and this is addition operation. So it is going to take constant amount of time, right? But that will be for given I. So when I is equal to 1, it's going to do x is equal to x plus 1. It will take constant amount of time, O of 1. When I is equal to 2, again it's going to take O of 1 time. When I is equal to 3, again it will take O of 1 time, correct? So how many times it's going to take O of 1 time? So time complexity for this particular function is going to be O of 1, that is constant amount of time to perform this internal operation, into number of times we are performing this operation. How many times we are performing this particular operation? Well, it's n times, right? Because I is varying from 1 to n. So total time complexity of this particular function is going to be O of n. You need to think in terms of total number of operations that you are going to perform when you are computing a time complexity. Now let's look at the second example as well. Now there are two different variables here, I and j. Both of them are starting from 1 and ending at n. So this is going to take O of 1 time. A constant amount of time basically. This we just saw is going to take O of n time. Correct? Now this O of n time will be when I is equal to 1. When I is equal to 2, the inner loop again going to take O of n time. When I is equal to 3, again it's going to take O of n time. This will keep on happening when till I is equal to n. Correct? So the time complexity is going to be O of n into total number of times this internal code, this internal loop is going to get executed, and that is n. Correct? That's why the total time complexity for this function is going to be n squared. I hope this is clear. Now there are 4 different loops here. We are going to focus on them one by one so that you can understand time complexity in a much better way. Let's look at the very first example that we have, right? So it's starting from 1, ending till n, and we are always multiplying by 2. So initially the value of I is going to 1. After that it will become 2. After that it will become 4. After that it will become 8. See, we are always multiplying by 2. That's why value of I is going from 1 to 2, 2 to 4 and 4 to 8. And this will keep on happening till we reach n. We have already seen multiple times this will take log n base 2 steps, right? Remember, log x base k represents how many times you are going to divide x by k till it reaches 1. We are multiplying 1 with 2 till it reaches n. Or we can see it otherwise as well. We are dividing n by 2 till it reaches 1. That's why the time complexity of this is going to be log n base 2. So it's not the case that you will have always O of n time complexity whenever you see a for loop. This is the biggest misconfusion that people have about time complexity. They see the for loop and they think that for loop always have O of n time complexity because here we have condition of less than or equal to n for I. But that's not the case. Look at how I is getting updated as well. So time complexity of this particular loop is going to be O of log n. I hope this is clear. If this is not clear, please watch my math basics video. I will put that into the card. Look at the inner portion. We already know the time complexity of this inner portion is going to be log n base 2. We just saw this, right? This is exactly what we have here. I will shift it a little bit. See, this is exactly what we have here. Here j is starting from 1. It ends at n and j is getting multiplied by 2 always. So the value of j will exactly grow something like this, 1, 2, 4, 8 till it reaches n. The time complexity of this inner loop is going to be log n base 2. Now how many times this inner loop is going to get executed? Well, it's going to be n times, right? See, when I is equal to 1, the time complexity of inner loop is going to be log n. That's the number of times this inner loop will get executed. When I is equal to 2, again it will be executed log n base 2. When I is equal to 3, again it will be executed log n base 2. And this will keep on happening till I becomes n, log n base 2. So that means the time complexity of this is going to be n into log n base 2. Correct? Because this inner loop is getting executed n times. On the right hand side we have something similar. Look at the inner loop. We have already seen j is starting from 1 going till n and is getting incremented one by one. So the time complexity of this inner loop is going to be O of n. But how many times this O of n is going to get executed? But how many times this inner loop is going to get executed? See, I is starting from 1. It's reached going till n and it's always getting multiplied by 2. Correct? So initially I will be 1. The inner loop will take O of n time. I will become 2. The inner loop will take O of n time. I will become 4 now and inner loop is going to take O of n time. Why 4? See, I is getting multiplied by 2 always. So it will be 2 into 2 which is 4. Again I will become 8 and the inner loop will take O of n time. So how many times the inner loop will get executed? Well, we have already seen it's going to get executed log n base 2 times. So log n base 2 into O of n. That's why you have the time complexity of n log n for this as well. See, in this example, this inner loop is taking log n base 2 time and it's getting executed n times. That's why time complexity is n log n base 2, right? Here the inner loop is going to take O of n time. But how many times this inner loop is going to get executed? Well, that is log n time. That's why the time complexity is n into log n. Now let's look at our fourth example. I is starting from 1, getting incremented 1 by 1, but the ending condition is that I square is less than n. You take root on the both side, then I should be less than or equal to root n. That's why the time complexity of this particular algorithm is going to be root n. I hope this page is clear. Once you understand the time complexity of this algorithm is going to be log n, you can clearly see for left algorithm and right algorithm that it's going to be n log n. I have just mentioned this because this is standard. We use this a lot in factorization, in square root decomposition. We have a few algorithms based on this. But the thing is that it's getting started from 1, getting incremented 1 by 1, and it's going till I into I is less than or equal to n, right? We took the roots on the both the side, and this is what we got. I should be less than or equal to root n. The number of times this constant time operation is going to get executed is root n. That's why time complexity is root n. I hope this is clear. Next thing is about the magnitude. See, the time complexity notation that we have, O of n, represents or estimates the total time our code is going to take in terms of the input size. But it hides all the constant factors. What do I mean by that? See, this will run n time, correct? This will run 3 into n time, correct? And this will run n by 2. Why? See, I is getting incremented by 2 here, not by 1. So it will be 1, then 3, then 5, then 7, something like this, till it reaches n. So this will be getting executed n by 2 times. But when you ask me what is the time complexity, well, the time complexity is going to be O of n. See, this big O notation doesn't care about the constants. So this is going to be O of n, and this is also going to be O of n. Now you might be wondering, okay, we removed 3 here, we removed divide by 2 here. So why did not we remove this log n here? Why are we saying this is n log n? Why are we not saying this is just O of n? Right? When it is 3 into n, we say it's O of n. When it's n by 2, we say it's n. But when it's n log n, we are not saying it as n. Right? We are still sticking with n log n. Why is that? See, remember the definition of the time complexity. It estimates the total time code is going to take in terms of the input. In 3 into n, we are removing this 3 because it is independent on the value of n. Value of n is 10, well 3 remains 3. Value of n is going to 100, it's not going to get increased, it's still 3. But here log n will change its value based on the value of n, correct? N log n, when n is 100, the value of n will change, the value of log n will also change. For n is equal to 1000, the value of n will change, the value of log n will change, correct? So big O notation hides all the constant factors but keeps all the values that are going to change when the input size is changed. I hope this is clear. This is very crucial to understand. Now imagine you have a function f of n, correct? We need to compute the time complexity of this entire function f of n. Whenever you want to compute the time complexity, the very first thing that you do is you divide the entire code into different phases. Now look at this particular phase. For loop is starting here and is getting ended here. The total time complexity of this for loop is going to be O of n. We have already seen it. I starting from 1, getting incremented 1 by 1 and reaching till n. And there is a function inside for loop that is taking constant amount of time. So it's ultimately O of 1 into n. Correct? That will be O of n. Again, you have another for loop. Starting here, ending here. Okay, so this is going to be one phase. The inner is constant. It's going to take O of 1 time. The for loop will be executed log n time. We have already seen it. I is getting multiplied by 2. So the time complexity of this is going to be O of log n. Again, The for loop is starting here and it's ending here. So this is going to be another phase. Inside this we have this for loop, and this for loop is going to take O of n time. We have already seen it. Why? Because j is starting from 1 going till n and getting incremented by 1. So the total time complexity of this inner loop is O of n. Now this O of n, that is the inner loop, will get executed n times because I is starting from 1 going till n. So it's going to be n into n, that is O of n square. So these three are the different phases: phase 1, phase 2 and phase 3. All of them are present in this function only. This function getting started from there and ending here. The very first loop is going to take O of n time, second is going to take log n time, third is going to take n square. So ideally time complexity should have been n square plus n plus log n, correct? This should have been the case, correct? But when we denote in terms of O, well, we remove all the slow moving functions from our time complexity. So this n will move very slowly compared to n square as the value of n grows. Similarly, this log n will move very slowly compared to this n square as the value of n grows. So when we represent in terms of O, we remove all the slow moving variables. That is, this n will be removed. Why? Because this is slow compared to n square. And this log n will be removed. Why? Because log n is very slow compared to n square. So the total time complexity of this particular function, which has 3 different loops with 3 different time complexity, is going to be O of n square. What happened to n and log n? Well, they got removed because this is getting added, right? And this n will move very slowly compared to n square, and this log n will move very slowly compared to this n square. So the total time complexity of this function is going to be n squared. Now what if you have multiple variables? We have some constant time operation here. So I am going to write here O of 1, correct? But now this O of 1 will get executed m times. Why? Because j is varying from 1 to m. So you will have m. Now this entire inner loop is going to take O of m time. Now if you look at the outer loop, it starts from 1 and end at n. Now if you look at this outer loop, I is varying from 1 to n. That means this entire inner loop will be executed n times. So it will be n into O of m. So the time complexity is going to be n into m. So for this particular phase, time complexity is going to be O of n into m. Why I am calling it as a phase? Because this for loop starts here and ends here. Finish. The job of this for loop is finish. It's not going to impact in any other operation that we see further, correct? Now you have one more loop here, which is dependent upon p. We have already seen the time complexity of this type of loop. It's going to be log p. So now time complexity of this first phase is going to be O of n into m. The time complexity of this second phase, the loop on p, is going to be O of log p. Now whichever is higher, if this n into m is higher, then we'll call this as the time complexity of the entire function. If log p is higher, then we'll call this as the time complexity of the entire function. Whatever is the max, we take it. Now in this video, we managed to learn the definition and basics of time complexity. In an upcoming video, we are going to deep dive into the most crucial part of time complexity, which is to compute the time complexity of a recursion. For a beginner, it's hard to compute the time complexity of recursion. That's why they fail to understand the importance of dynamic programming as well.